Good afternoon, ladies and gentlemen. Welcome to the 4th annual Taira Prize lecture. This is the 4th year that the lecture has been given, and also I think it's a lecture celebrating the wonderful 50 years of ocean research drilling that we have listened to some talks earlier in this week. For those of you who are not familiar with the Asahiko Taira International Scientific Ocean Drilling Research Prize, it is in recognition of outstanding interdisciplinary research accomplished in ocean drilling. And this award is given in partnership with the AGU and the JPGU, and it is set up to honor Dr. Asahiko Taira of the Japanese Agency for Marine and Earth Science and Technology, better known as JAMSTEC. And Dr. Taira had an extensive background of more than 40 years in geological research. And many of us in this community are very familiar with his contributions. The prize is given for outstanding and transdisciplinary scientific contributions enabled by the ocean drilling. And its frequency is given 1 year, and as I mentioned before, this is the 4th time the prize has been given. The eligibility is very specifically limited to an outstanding young scientist, early career scientist, within 15 years of receiving his or her PhD in any discipline related to ocean drilling. And this individual must be making an impact in the field of ocean drilling. And as the chair, you might wonder why I'm standing here. I am the chair of the selection committee for the Taira Prize. My name is Judith McKenzie from the ETH Zurich, and it's my great pleasure to announce this year's winner is Dr. Brandon Dugan he is Associate Professor of Petrophysics and Borehole Geophysics at the Colorado School of Mines in Colorado. And in commentation, he is the recipient of the 2018 prize for his ocean drilling leadership and outstanding contributions on the role of fluid-porous media interaction on slope stability and seismogenesis. And to introduce Brandon to this audience, I would kindly ask Marta Torres to stand here because she nominated him and is more familiar, having sailed with Brandon, more familiar with his research. So please, Marta.
Okay, thank you. Thank you, Judith, and again, welcome everybody. And it is always wonderful to see all the IODP people, also with a connection with the 50th year anniversary. And I am very happy to introduce Brandon as the recipient. He got his BS degree in geology in 1997, and then received the Joe Yusak Fellowship, which is the precursor to the current Schlanger Fellowship. And it is interesting or motivating to see the effect that these awards have on young investigators. He then went to finish a PhD in Penn State. His thesis, which is hydrodynamics of the continental slope offshore New Jersey, laid the fundamentals for some new interpretations and new understanding of the role of fluids, slope stability, continental morphology. His ideas were published in Science, and they laid the foundation for IODP 308 in the Gulf of Mexico that tested this idea. So ever since his young career as a graduate student, he has made good contributions. He has participated in 6 expeditions, both in the JOIDES and in the CHICU. I sailed with him for the first time in 322, looking at the input sections to the Nankai. Before that, he participated in 308, as I said, testing these ideas in the Gulf of Mexico. Then he sailed twice as co-chief scientist, one in 338 and 362. I sailed with him in 362, and I can say he was an outstanding leader, both in terms of being able to guide the science and to listen, and kept a really good environment together with Lisa McNeil. They did a great job. And then more recently, he sailed as a downhole expert in physical properties in 372. to just briefly summarize some of his achievements and the reasons that he is clearly a worthy recipient of this award. He did a lot of development of new tools, of new instrumentation and new techniques that not only leveraged his future research scientific accomplishments, but also laid foundation for the community to advance science using his technology and instrumental contributions. So he developed a pore penetrometer and used new techniques using the logging while drilling data to estimate permeability. And then here I listed only 3-4 examples of some contributions that he had made to the field in terms of understanding pore pressure evolution, poromechanics and slope stability. He has also been contributed combining this experimental and technical modeling to gas hydrate and gas release, the formation of seeps, and the evolution of permeability during compaction. So these are very brief mentions of some of the contributions he has made. And I have a couple of pictures of Brandon. This is during Expedition 308. As you would see him in the bottom as a young graduate student working with Peter Flemings on the Gulf of Mexico expedition. And then in the next slide, there are some pictures from Sumatra. He was a co-chief, as I said, in 362, and there he is with Lisa and in the co-chief office that you probably recognize, and also the other picture shows him working with the downhole tool in Expedition 372. One other set of pictures as co-chief, one of the big responsibilities is to judge the kite contest, which he did very efficiently during 362. I just wanted to show him working with the curator, collecting samples, because he's, has no problem getting his hands dirty and helping wherever it is needed. He's really a wonderful colleague to work with. So besides his scientific contributions, he's also a wonderful leader and colleague to work with. He has, I think, an excellent record of mentoring young people. This is here with his student. I think this was 372. But there are many other examples of where he has notoriously contributed to training the new group of young scientists that participates in the program. And so I have a list here of his leadership and outreach. The prize, as it is described, highlights not only the science achievements, but also the contributions to leadership and the community as a whole. And he definitely, go back. He definitely has done quite a bit of this. He has been working as a panel member in several groups, he's been a steering committee in a variety of groups as well. And I wanted to highlight that his engagement in the early career for future scientists, just another example of his mentoring and enabling of the new generation. So this is just my last slide. This is the last core from Expedition 372, where he's helping carrying the last core to the catwalk. And with that, I would like to ask Brandon to come to the talk and to the podium and give us his presentation on understanding shallow subsurface fluid flow in marine sediments through coring, logging, experiments, and models. Brandon.
And the beautiful medal will be given to Brandon at the celebration, the honors celebration this evening. So we hope many of you will be there in attendance.
Thank you, Judith and Marta, for that wonderful introduction. I'd also like to thank the AGU and the JPGU for creating the Taira Prize to recognize early career to mid-career scientists for their contributions to scientific ocean drilling. But in reality, none of this would have been possible without the contributions of IODP to my career. I've had the opportunity to sail 6 times, first as a graduate student, and I had many mentors who taught me how to think critically, how to edit papers efficiently and quickly, how to discern observations from interpretations, take things from the ship, and bring them out to scientific papers in the end. And it's been a wonderful 15 years since I started in this program. And I want to give you a little bit of a highlight today of some of those things. And this is contributions from 6 different legs and expeditions. And I'd like to thank all of the science party members on every one of those expeditions, but also the technical staff and the ship staff. Those who've sailed before understand that we couldn't do what it is that we're able to do without all of the support that we have technically. So thank you to all the co-chiefs, my advisors, mentors through time, and I hope I can give back what's been given to me so far in IODP the last 50 years, and I look forward to 50 more. So an overview for the talk today, I'm going to start out with an introduction of the motivation of a lot of my early career research, looking at shallow fluid flow in marine sediments, an example of interpretation of that fluid flow system, then moving on to an assessment of that flow system with expeditions 308 and 372. Then I'm going to transition into a little bit of geochemistry and how I, not a geochemist, can link geochemistry to fluid flow properties and learn from people like Marta on the ship. And then I'm going to end with a couple of slides about one project that I'm interested in pursuing in the future of looking at freshwater as analyzed through scientific ocean drilling. Sort of a unique concept if you think about it, freshwater beneath the ocean. So the idea before shallow fluid flow in submarine environments started many years before I looked at the problem. Starting as early as 1939, Johnson was looking at canyon formation and headward erosion on the continental slope, and he related it to fluid flow recharge onshore coming off and being discharged. Peter Rona looked at this again in 1969. You have high fluid pressures, generates sediment instabilities, and then you get headward erosion up towards the shelf slope break. Shepard and Prattson looked at this in a slightly different way, where you could get local oversteepening at the shelf slope break and driven by fluid flow and have failures, and then have downslope erosion. We're going to look at a similar system, but what if the aquifers or the flow unit is not connected all the way across the slope? How do you generate these failures? Where do you get the fluid pressure from? So this starts, also links to submarine landslides. Here's an example for the Storegga slide. Many of you know about this off the coast of Norway. There were tsunami deposits, 8,000 years old, in the northern United Kingdom that were proposed to be displaced by a tsunami generated by a submarine landslide. But what caused a submarine landslide was a big question. We're looking at scales on the order of hundreds of kilometers for these landslides. Other work looked at the Sahara slide, and what I like to point out about this slide, it's the same sort of length scale, hundreds of kilometers, but when you go in and you look at the continental slope, it's sloping at less than 1 degree continuously. So there was a big question to be asked of, why do these low angle slopes fail? 1 or 2 degrees, they should be stable, there shouldn't be any slope failures, and why are they so large? And that was sort of where I started my foray into scientific ocean drilling. From data through IODP Leg 174A, off the coast of New Jersey, sort of the making lemonade out of lemons problem. There were some earlier sites drilled, they had problems. They moved out onto the slope and drilled an alternate site between the Hudson Canyon to the east and these other smaller canyons to the west. And we started looking at, well, what role does active fluid pressure and fluid flow play in the formation of these canyons, or what could it portray? So I'm going to show you a seismic cross-section, A to A prime, to show you what the stratigraphy looks like. So here's two-way time, 2 seconds, about 25 kilometers across for the seismic section. And the interpretation, here's the seafloor, here's the Pleistocene-Pliocene boundary, here's a Miocene-Oligocene boundary. And generally, if you look at it, it's pretty layer cake stratigraphy. When you get in and dive a little deeper, you can actually see some small-scale slumping features and deformation features, and this is where Peter Flemings and I started to volley back and forth ideas about what is driving this deformation, and does it relate to canyon failure, canyon formation, or slope failure? And so we started looking at the shipboard data. Here's 1073 down to 650 meters below the seafloor. Here's the interpreted shipboard lithology. And here's the void ratio going from low to high, or you can think about it as porosity from going low to high. And all the dots are the MAD data points. And what you see is that porosity starts with a decrease, but then it becomes relatively constant. There's some areas of increase, and then it decreases a little bit more, and then it increases again, 60% porosity at 600 meters below the seafloor. And one way that you could hold those pores open would be with very high pore fluid pressure that could lead to instability. So you can constrain a model for what the normal compaction curve is, relating porosity and stress, and predict what the pressures are that would keep these pores open at this ratio. And so we constrained a model at 100 meters and then use that higher porosity to predict pore pressure, so it was a modeling approach. We also took some of the samples back to the lab and squeezed them. So here's porosity from high to low and vertical effective stress. We take a sample back to the lab and we squeeze it vertically and measure the stress-strain relationship, and it starts out early with an elastic portion and then rolls over onto this elastoplastic region. And this change in curvature tells us what the in situ stress of that rock could be, from which we can back out the in situ pore pressures. So when you take those porosity data and those geomechanical data, you can make a prediction of depth versus overpressure. So here's the hydrostatic axis going vertically here. The dashed line is the reduced overburden stress, so just the weight of all the water and rock above us. And this black line is the interpretation of the pore fluid pressure from the porosity stress model. And we see that there's significant overpressure increasing with depth. These colored dots are different interpretations of those geomechanical experiments where we squeezed the rocks and interpreted the pressure from the pre-consolidation stresses. And so what we did was we came up with this prediction that there were very high overpressures in this section, and potentially it relates to canyon formation or slope instability, but it's all based on interpretations of mechanical behavior. And this laid the foundation for IODP Expedition 308, where we were looking at the Ursa region in the Gulf of Mexico, 200 kilometers south of the Bird's Foot Delta, where we were trying to look at the origin and magnitude of these shallow pressures. So rather than just interpreting them, try to figure out how they got there, and then how they relate to the initiation of slope failures. And this was a great place to do this test because the oil industry, primarily Shell, had worked with us closely, showing that there were slope failures there, and there were evidence of overpressures beginning near the seafloor. So it was a great testing ground for our previous interpretations. Just to show you what some of these slope failure deposits look like, here's two seismic sections through the wells that we drilled. Two-way travel time. This was a half a mile for scale. Here's the seafloor, relatively layer cake stratigraphy. But then you see down here there's a bunch of discordant reflections, and these are slope failures that were believed to be initiated by rapid sedimentation and overpressure, and we were out there to test that model, not only measure the pressure, but the rock properties and understand it. And when we move a little bit to the east, we see also more deformation below the seafloor. Here's the seafloor coming in here, 1323 drilled through here, and we actually see a different type of deformation, actually brittle deformation in these marine muds that are less than 60,000 years old. So we see different types of deformation, very discordant reflections here, and almost a domino block-like rotation here. And so we started looking at what role does pore pressure play in the initiation of failure, but also the types of failure that we observe. And so Justin Stigl, one of my graduate students, worked really hard on this, and it was a lot of fun working with him to do this. But we started out with a simple conceptual model of what the hydrostratigraphy looks like. So we took that seismic cross-section and simplified it down into three lithologies, starting down here at the bottom. We have some sand units called the blue unit, and they're a series of stacked basin floor fans that are regionally extensive. So you can think about these as connected aquifers throughout the basin. We have some channels, Ursa Canyon, Southwest Pass Canyon, and levee deposits, and then we have mud on top of it. So we broke the system up into three very simplified lithologies and tried to say, how would the pore pressure evolve in this system? And it's elegantly described by this equation, which basically just says we're going to try to model the change in pressure with time as a function of the Darcian flow in and out of the system, and accounting for any pressure sources that are added to the system. So this could be rapid sediment loading where the rocks want to squeeze, but the fluids can't get out, so the fluid pressure gets up, or thermal expansion. And if you look at a very simplified 1D model, you can start out with this isolated sand package buried in clay. And as it gets buried deeper and deeper, you get a little bit of focusing into the sand and then out, but it's predominantly a vertical flow field. But if you have a differential geometry like we have in Ursa, or like we had in the Gulf of New Jersey section, where we have thick sediment loading over here and thin sediment loading over here, what you do is you create a very high pressure field over here, drives flow through the path of least resistant, and it wants to be discharged along that place. And we started looking at the game of how much pressure can be generated, how is that pressure transferred around, and how does it relate to slope stability. You need to know a few things, and I'll explain these most simply for the model with my favorite little simple analysis. Here's our aquifer down here, and here's the representation of that aquifer. We have a small amount of loading over here. On this side, I add a bunch of energy very quickly with somebody jumping on. That pressure is rapidly transferred over to this side, and the student is launched off the side. That's the slope failure, right? But it depends on a lot of things. It depends on how quickly the pressure can be transferred from left to right, or from 1324 to 1322. So we need to know something about permeability. How quickly can the energy be transferred from one side to the other? We also need to know about how quickly the load is applied. If this person climbed down, there would be no or little impact over here. So the sedimentation rates are important. And we also have to know what the response of this is to a load. Is it really squishy, like when it's filled with air? Or if we were to fill it with a bale of hay or something like that, it'd be less squishy. There wouldn't be as much deformation. So we need to constrain the loading rate. We get that from the biostratigraphers. But we also need to know the permeability of the system and the squishiness of the system, the compressibility. And then we go back to the laboratory to run those experiments to understand that. So here's the compression index, how squishy the rock is. Very squishy up here, less squishy down here, as a function of void ratio, going from low void ratio to high void ratio. And we get constraints from the laboratory about how compressible the system is as a function of its porosity state or the stress state that it's at. And we can input that to our model. We also get measurements through these experiments of permeability, easy to flow, hard to flow, as a function of porosity, so we can break out our geologic units and get porosity permeability relationships. We take the biostratigraphy, sedimentation rates, and we can make a prediction of what the pore pressure should be in this system. And so we worked on this, doing this very simple model in 2 dimensions. Started out with a basal layer of silt and clay, and then we deposited these high permeability sand units. We eroded and deposited some canyon deposits, then another canyon deposit, and then we started hemipelagic drape on the top. So the geologic evolution imparted with the rock properties and the biostratigraphy allows us to say, what would the flow field look like if we know all those input parameters, and how does this relate to slope stability? The output is shown here. Here's our modeled location of 1324. Here's our modeled location of 1322, and this color scale is overpressure, so hydrostatic pressure in white, and red, hot colors are high overpressure, and it matches the conceptual model. Where I have a lot of loading, I get high fluid pressures. Where I have less loading, I have lower fluid pressures, and I focus a lot of flow in those permeable units. Models are great. They give us a prediction of how we think the system behaves, but one of the exciting things that we did on Expedition 308 was actually go out and directly measure the pressure to see how well we were doing at forward modeling the system. So here's Peter and I and Wayne trying to pull a tool out of the borehole after it was lowered down to measure in situ pressures. Here's the tool that we would primarily use, the temperature dual pressure probe, about the size of a pencil down here. For those who've been on the ship, when you ask the tool pusher to put something the size of a pencil down the hole and stick it in front of the borehole, they're willing to do it, and they'll tell you it's not going to come back. We tried a lot. Some didn't come back, but a lot of them did come back. So we actually had direct in situ measurements of the pressure to test our models. And these are the results, just the comparisons. On the left, 1324 down to 600 meters below seafloor in an overpressure plot again. The yellow line is the extracted pressure prediction from our fluid flow model, and all the red dots are interpretations of the pore pressure from direct in situ measurements. So it's sort of a huge step forward from leg 174, where we're just interpreting the pressure. Here we actually have measurements. And you can see in the upper 200 meters, our model is doing quite a good job matching the pressures that we measured. There's a discrepancy at depth. I'm not going to talk about those today. We're going to focus on the landslides because they happen up here. How does that pressure relate to landslides? In 1322 down to 250 meters, again in those upper 200 meters, we do a very good job with our model predicting the in situ pore pressures. So this was a huge victory in terms of testing a hypothesis that drove a drilling project and actually documenting that overpressures exist near the seafloor. It doesn't have to be a kilometer down or 2 kilometers down. And you can do some stability analyses. So we're just going to look at this surface right here, the 27,000 year surface. So moving west to east across our model domain, 27,000 years to present. And these contours are stability contours of whether or not this slope should start sliding, relating the frictional resistance to the driving forces. And any number that is less than 1 suggests that the slope would fail under the current pressure and stress conditions. And what you see is throughout the entire deposition of this above this surface, there's no slope failure on it. Yet in the geological record, we see a huge mass transport deposit that has variable behavior across it. So our overpressure preconditions the slope, but it's not able to drive failure. So we started to look at what else might drive failure in this system. And we started looking at the earthquake catalog for the Gulf of Mexico. So within about 100 kilometer radius or 120 kilometer radius of the region that we studied, we looked at earthquakes. And in the last 50 years, there have been magnitude 3, 4, and 5 earthquakes shown up here as the dots. And we looked at how much horizontal acceleration those earthquakes could impart on the slope at different times and take this weakened slope by overpressure and drive failure. And what we saw is that if you had a magnitude 5 earthquake, as those sediments were being deposited 27,000 years ago, any earthquake within this red dash would generate slope failure for those conditions. Inside this turquoise dash, any magnitude 4 earthquake would drive slope failure at 27,000 years ago. If you let sediments accumulate for a few years, a few thousand years, you need a magnitude 5 earthquake within about 20 kilometers of the Ursa region to drive slope failure. So it's not a definitive answer that earthquakes played a role, but it's reasonable to suppose that there were earthquakes of that magnitude at that time frame that triggered the slope failure only under the conditions of elevated pore pressure from sediment loading. We've continued to look at this in different environments. Last December, many of us in this room were out on Expedition 372 on the Hikurangi margin. Here's the Tuahini landslide, a very large landslide complex that appears to be actively creeping today. It has regions of extension and regions of compression, shown here in the sort of northwest to southeast cross section. Here's the base of the landslide. There's gas hydrate stability here. We see compression and we see extension. And the goal of one of the goals of Expedition 372 was to investigate this creeping failure behavior, its relationship to overpressure, and its potential relationship to gas hydrates. I'm going to talk more about this on Friday with many other people who are studying 372, but I'll show you some of the things that we have observed now. So looking at pressure, permeability, and compressibility. Here's depth. Here's the MAD porosity data here. When you interpret the geomechanical experiments, some of these are compliments of Michael Knoll at University of Texas, now at Sandia Labs. We can interpret the pore fluid pressure, and we see in the landslide above, most of the pore pressures are approximately hydrostatic or even subhydrostatic. I don't actually believe they're subhydrostatic. I think it's a deformation effect from not being vertically loaded. But when we move down into the gas hydrate stability zone, we start to see evidence of overpressure beneath the slide, potentially playing a role in that slide. We also see separation of rock properties. So here's permeability and compressibility, and we see different behaviors within the slide mass and outside the slide mass. So we now have initial data that we can correlate with the lithology and start to think about forward models and what's creating this creeping behavior of the Tuahini landslide complex. Switching gears a little bit, looking at subduction zone inputs, where I first started working with Marta. Expedition 322, part of the Nantrasize expedition, a multi-expedition currently out drilling today, trying to understand plate boundary behavior on a megathrust. Expedition 322 focused primarily on these sedimentary inputs, C0011 and 12, and what are the evolving properties of these input sediments that may localize a décollement horizon, how is it related to fluid pressure and fluid flow. So I'm just going to focus in on some geochemical analyses and some back-of-the-envelope calculations we did for fluid flow behavior. So here's the methane and ethane for C11, moving down to about 850, 900 meters below seafloor. And we see in both cases the very low concentrations in the headspace gases, and then this rapid increase to a peak along a very specific stratigraphic horizon. And when we look at C12, farther seaward, we also see a similar behavior, very, very low concentrations in methane, and then ethane spikes out on the same stratigraphic horizon where we see this spike in methane and ethane at C11, and we see the same spike in C12. So I started with some very simple diffusion modeling to say, if we held that horizon at a constant concentration, how long would diffusion take to create this profile that we observe? And for C11, it takes about 750,000 years for diffusion to create that profile. It fits the methane and the ethane very well. For C12, if you run the same analysis, the diffusion time is about 80,000 years. So the same stratigraphic horizon is sourcing these behaviors, but the diffusion times are less. So one interpretation might be that the methane and ethane sources has to transfer from C11 over to C12. So it looks like some of these permeable horizons that extend across the basin are transferring fluids advectively from one location to the other on the orders of millimeters, 10 millimeters per year. So it looks like even far seaward where there's not rapid loading, there could be an advective component. This might influence localization of horizons, et cetera, for the décollement moving into the subduction zone. So it's many years ago, and there's still lots more work to be done thinking about this. More recently, with Lisa McNeil, I had the opportunity to go out to the Sumatra subduction zone and drill the sedimentary inputs to the plate boundary that generated the 2004 earthquake. And we were looking at seismogenesis, tsunamigenesis, and forearc development. A very ambitious program considering we were drilling the subduction zone inputs. But again, the logic is the same. What are the properties of these input sediments that lead to this subduction zone architecture and also the broad and strong accretionary prism? We had an excellent science party on this project, and here's just the regional geometry to show you. So here's depth or time on this axis, and the cross section 200 kilometers plus. Here's the deformation front, thick sedimentary package going into the subduction zone, and we're drilling 200 kilometers seaward of that. And the idea was to think about what are the physical properties, the chemical behavior, and flow behavior of these sediments as they move forward and are incorporated into the subduction zone. How does this favor the significant amount of slip that happened seaward of the trench, or very seaward of the trench in this experiment, and the massive rupture that created the magnitude 9+ earthquake? And we're going to look at some geochemical data that came out during the ship and was, as Marta reminded me before this, much of this work was done in an unplanned transit to Singapore. And we're going to look at some of the geochemical data again, but here we're going to look at chloride anomalies, and rather than looking at increases, we're going to look at decreases. So here's 1480 and 1481, two sites we drilled. And in both sites you see high chlorinity values moving down, and then you start to see these decreases in chloride behavior. We've seen this in other subduction zones around the world, and you see the same thing at 1481, chloride relatively constant, and then we see these decreasing behaviors. Andre Hoypers led the charge for modeling this behavior. And the first thing that he did was try to figure out how recent this anomaly was, or this anomalously low chloride behavior. And so he did some diffusion modeling similar to what we did on 322 and tried to look at the time scales to match the observed trends. And the net result is this freshening effect has to be less than about 100,000 years old. So it's a relatively recent phenomenon where we're actually seeing some reactions that are creating fresh water and then diffusing away. So it's a relatively recent phenomenon, and we tried to understand more about what was going on. Andre then extended this. Now we're looking at a slightly different path. So looking at Site 1480, one of the primary sites, and its evolution in temperature from 40 million years ago as it starts approaching the subduction zone until it reaches its location today and ultimately gets incorporated into the subduction zone. So there's a temperature component of what's the temperature of those rocks at depth as they're being buried, and then looking at the different sources of fluid production and the chemical implications and the strength implications of those fluid production. This green line shows fluid production from compaction, so sediment loading, what we looked at for the Gulf of Mexico. And there's an early pulse of sediment, and then that production dies off, and then there's another pulse of sediment when the Nicobar fan starts being deposited, and then that pulse decays off, and then there's another pulse when the trench wet sediments start being deposited. So compaction is a small percentage of the fluid source. And then we also look at the opal A to opal C transition, and there's some plagonite in these rocks, so we look at smectite fluid production as a proxy for that, and this was the most exciting part. What Andre showed is that the dehydration reactions from opal A to opal CT go to completion, very close to where we were looking at the sediments today. So there's a recent behavior given the depositional environment and temperature environment that we know, and most of the smectite or palagonite is also completely dehydrated before it reaches the deformation front. And so we can explain the chloride anomaly by these geochemical reactions and the temperature history. The models predict complete dehydration of opal and palagonite before it reaches the deformation front, so much farther seaward for complete dehydration than we've seen in other zones. And this actually results in a strong décollement, the geochemical changes, and this can promote unstable slip, potentially facilitating this very large earthquake that happened in 2004. Now, sort of for the last phase of the work I've done in the past is a proposal that I hope to drill in the future. And this is looking at global offshore freshwater resources. Each one of these dots is a location where freshwater has been interpreted to exist below the seafloor. So freshwater resources beneath the ocean. Based on well log data or other pieces of information. It's been observed, Expedition 313 off New Jersey, Canterbury Basin off New Zealand. We've seen this freshening 10, 20, 30, 40, 50 kilometers offshore where you have drinking quality water extending beneath the ocean. And the question is, how did it get there? How much is there? What's the local plumbing system? Unfortunately, there's never been a dedicated expedition to this. This is sort of the state of the art of how this water's been understood. This is from the 1970s when the USGS was inventorying mineral resources, hydrocarbon resources along the Atlantic coast, and they started sampling water on the ship and realized it was fresh. And we started looking at this to try to understand what could potentially be causing this freshening, and how could this be used as a resource in the future if necessary. And so started with, again, a conceptual modeling. If we think about an equilibrium condition, here are some islands and some land. We have sea level sitting out here, and you can just use the Geibin-Herzberg principle to estimate where the fresh water should exist, at what depth beneath land, and you won't see any fresh water extending even in aquifers very far offshore, maybe tens of meters driven by local topography. But sea level's not constant over time, and neither is climate, so we started looking at the impacts of that. During glacial low stands, sea level is lower, so you have meteoric infiltration, topography changes, and you can actually charge aquifer units that are now exposed, and then sea level rises, and they've been flooded again. So we can think about how much fresh water is put in by meteoric recharge, local topography, and local flow cells, and how it's different from modern day equilibrium. At high latitudes, we can also think about big ice sheets marching out onto the shelf, increasing the potentiometric surface at the base of the ice sheet where meltwater is being produced. This drives fluids laterally out, potentially, and then that ice sheet backs up. When it melts, inundation happens, and that fresh water gets trapped beneath the ice sheet, or beneath modern sea level. So we've done a bunch of work looking at, this is Cape Cod, Martha's Vineyard, and Nantucket. We started by collecting seismic data to understand the regional stratigraphy. We want to understand where the flow units are, what their stratigraphic architecture is, and developing a drilling proposal to sample freshwater, sample the freshwater seawater transition, and look at different seawater zones to understand the temporal variation of this boundary and how it might be imparted. There's a seismic section down to 800 meters. It's about 100 kilometers across, and we have the regional stratigraphy fairly well defined. We have these shallowly dipping layers, then we move over to some cliniform layers, and there's a big erosional unconformity coming across here that we believe is glacial in origin. Jake Siegel did a bunch of this work in 2012. And then we have progradation of cliniforms out on top of that, and then another erosional unconformity, and then most recently glaciogenic sediment coming out in this region. So we have the stratigraphy defined. We think this unconformity defines the glacial extent. Now we think that the glacier extended approximately 100 kilometers offshore, significantly farther than previously expected. And we have ideas then about what the driving forces could have been for this flow system, and wanted to look at the geochemical variation from this, and these are proposed drill locations to understand this. So we integrated all those 2D data sets to come up with a 3D hydrostratigraphic architecture, similar to what we did in the Ursa region, relating lithologies into very simple packages to permeability and compressibility. And we have this start out with these old carbonate muds, and these big silty clay packages, and unconformity, glaciogenic sediments on top of that erosional surface, and then some clay layers and some outwash. And we can go ahead and forward model what this loading system looked like and look at the pressure like we did in our previous examples, but we can also look at the sources of fresh water from the base of that glacier and how the freshwater distribution might look. So here's 2 conceptual experiments that we ran. This is very simplified geometry. There's that glaciogenic unconformity. We have dipping stratigraphy beneath it. We have some bright spots in the seismic that we think are expulsion features, so we have some pressure information. And we could just forget about the ice sheet altogether, and we could look at sea level variations and deposit Pleistocene sediments and figure out what the freshwater would look like just from an exposed shelf. Or we can look at an ice sheet that extends out onto the shelf. Meltwater at the base gets driven out and discharged in front of the toe of the ice sheet, and then that ice sheet retreats. How does the flow system evolve for that? I'll just show you one model result. So this is the present day estimate of freshwater in that 3D volume. There's potentially 100 cubic kilometers of freshwater that could be used. It's non-renewable, but it potentially could be used in times of need, maybe summer season. As climate changes, Massachusetts is actually pretty concerned about their water resources during climate change right now. And this is a prediction of the model results. Blue here, drinking water quality. Red, 35 parts per thousand, so seawater salinity. And we can see that there are these big pockets of fresh water extending 20 to 30 kilometers offshore. Then we have this transitional zone where it's sort of 10 parts per thousand, so not fresh water, but not seawater, so potentially useful for some activities, or could easily be desalinated, or more easily than seawater, and then transitioning into the seawater zone. And it all is driven by these ice sheet conditions. These arrows up here, last glacial maxima is where we think the last glacial extended, and that previous glacier that we looked at stepped out here about 120 kilometers seaward of the extent. We've run simulations for sensitivity studies. If we take this ice sheet out, the present day freshwater decreases by about a factor of 4, so it gets down to about 25 cubic kilometers of freshwater. So even if the glacier didn't come out 120 kilometers, there's still a lot of freshwater sequestered in this environment. We also look at no glaciation at all, seawater only, and it comes down to about 7 cubic kilometers of freshwater. So there's potentially freshwater sequestered out here. Chloe Gustafson, who works with Carrie Key at Lamont, has gone out and done CSEM and magnetotellurics analysis out here, and they see resistivity anomalies that are consistent with the freshwater distribution coming out to about this location. So now we have another data stream to go out and test this, and the ultimate test, just like the pore pressure prediction from the Gulf of Mexico, will be to go out, drill these sites, sample these waters, and look at the isotopic analysis to try to figure out their origin and their age. So I'd just like to leave you with a few closing thoughts. One is fairly broad. Shallow fluid flow is important for geomechanics, margin evolution, hazards, and chemical fluxes. I think this is probably not surprising to all people, but I think the most important part is these flow processes happen starting at the seafloor in many environments. So shallow really is at the seafloor here, and this is something that I think we've learned through scientific ocean drilling in the last 20 years. For the younger people in the audience, ODP, IODP provides an avenue for science, mentoring, and I think most important to me is depth and breadth. I came in with a very narrow focus. If you remember the start of my talk, it was all computationally based. I got involved in building tools, collecting seismic data, learning about geochemistry, and actually collecting samples. So it's created a well-rounded approach for me and hundreds of great quality colleagues with whom I can work. And I think the most important thing that I've taken out of the last 20 years of drilling for my life is, it's important to step outside of your comfort zone. It was very comfortable for me to sit in front of a computer and model whatever I wanted to model. And now I can embrace new things. I continue to learn. I've ventured out from being a physical hydrogeologist to seismic processor, seismic interpretationer, geochemical collaborator, geomechanics person in the laboratory and in the field. So for those who want to change, ODP, IODP provides a mentoring structure and nurturing structure that allows you to do that. So I'd like to thank everybody who's helped me get to where I am today, and I look forward to working with you in the future. Thank you very much.
Thank you very much for the stimulating and challenging talk. Thank you very much. We do have some time, so if there are any questions in the audience, Jamie?
Brandon, what's been the biggest surprise?
The biggest surprise, I think the biggest surprise to me is that, and this is for somebody that overpressure is near and dear to their heart, is it's not the answer to everything. If you go back and read the literature,
there's the answer to everything.
But if we go back and read the literature and talk to people, there are these throwaway sentences, myself included. Overpressure generated the slope instability. Overpressure facilitated the flow on the fault or the slip on the fault. But when you actually go out and measure it and start interpreting it and really try to integrate the physics, often it's nearly impossible to generate that amount of overpressure. It gets you close, but not all the way. So this is where we have to integrate other pieces of information. So we've been able to quantify it. It is important, but it's not the total answer.
Further questions? Further questions? If not, I want to thank you again for this lovely presentation, and thank you, Marta, for the nomination. And to remind everyone that we have another contest coming up next year for the next Taira Prize, and we hope you will be thinking of some of your young colleagues that you would like to nominate. Furthermore, I hope to see many of you at this celebration tonight, the honor celebration, where Brandon will receive his beautiful statue, and also we can celebrate with a glass of bubbly with Brandon afterwards. So please come tonight. Thank you.
Thank you, Judith. Thank you, Marta. Thank you very much.